Assalamualaikum and hi. In today's video, I will give an introduction and basic concept of materials thermodynamics. So you will learn about the power and breadth of thermodynamics. Evidently, there is a broad agreement that this subject is a central one in materials science and engineering. Likewise, this same statement can be made for programs in chemical engineering and chemistry, maybe to a lesser extent in physics. So why you should study this course? Why you should study thermodynamics? I know most of you here have already did your thermodynamic course from your diploma studies or maybe foundation. But you still need to study thermodynamics of materials because in this course, you will study the application of the thermodynamic concepts to the analysis of phase equilibria, phase transformation, and phase diagrams, starting from one component until multi-component systems. This is in turn very important for development of new materials, improvement of the current materials, for processing of materials, and lastly, in understanding materials in general. So take a look at this slide. There are 5 primary reasons on why you need to study thermodynamics. First of all, thermodynamics is pervasive. It is also established and comprehensive. Thermodynamics provides the basis for organizing information about how matter behaves. And lastly, thermodynamics enables the generation of maps of equilibrium states that can be used to answer a prodigious range of questions of practical importance in science and industry. So let us take a look one by one. Thermodynamics is pervasive. It applies to every volume element in every system at every instant in time. How pervasive can you get? The meaning of pervasive here is existing in or spreading through every part of something. And then we have thermodynamics, which is established by J. Willard Gibbs in 1883, essentially completed the apparatus of phenomenological thermodynamics in his classic chapter paper on the equilibrium of heterogeneous substances. The scientific and technological explosion of more than a century has not required a significant modification of Gibbs' apparatus. Thermodynamics is comprehensive. The apparatus is capable of handling the most complex kinds of systems, applications, and influences. So these systems here means something like metals, ceramics, polymers, composites, solids, liquids, gases, solutions, and crystals with defects. For applications here, like structural materials, electronic materials, corrosion-resistant materials, nuclear materials, biomaterials, and nanomaterials. The apparatus is capable of handling the most complex kinds of influences like thermal, mechanical, chemical, interfacial, electrical, and also magnetic. And then we have thermodynamics provides the basis for organizing information about how matter behaves. Thermodynamics identifies the properties of systems that are scientifically and technologically important in a wide range of applications. It identifies the subset of these properties that are sufficient to compute all the others. These are the properties that are measured in the thermochemistry laboratories of the world and have been accumulating in the databases of the world since Gibbs's time. The apparatus then provides relationships between these database properties and the functions that are crucial in predicting the behavior of matter. And last but not least, thermodynamics enables the generation of maps of equilibrium states for this broad spectrum of systems and influences. A variety of species of such maps are widely used in science and industry to answer real-world questions about the behavior of matter. This is the example of one of the generic questions addressed by thermodynamics. The example is, if you take system A in surroundings 1 and put it into surroundings 2, what will happen? So the rudimentary thermodynamics concepts implicit in this question include the system, which is the collection of matter whose behavior is the focus of the question. So you have system A and system B. Second is the surroundings, which is the matter in the vicinity of the system that is altered because it interacts with it. We have two surroundings here, surroundings 1 and surroundings 2. And then the boundary implicit in the concept of a system and its surroundings, which may limit the kinds of exchanges that can occur between the two. And then lastly is the properties required in the definition of the condition of a system and its surroundings. As an example of this generic scenario, first we consider a block of cadmium sitting on a lab desk so that its initial condition is ambient pressure and temperature, nominally at 1 atm and 25 degrees Celsius respectively. And then you pick up this cadmium and place this cadmium in a furnace, which has its temperature controlled at 545 degrees Celsius. So take a look at this figure. System A is the piece of solid cadmium. Surroundings 1 is the ambient pressure and temperature of the lab, while surroundings 2 is the atmosphere in the furnace, also at ambient pressure but a temperature of 545 degrees Celsius. System A here experiences a change in surroundings when it is placed in the furnace. As a result, System A begins to change its condition toward a final state B, which is in equilibrium with these new surroundings too. Equilibrium here means equal balance between any system, any powers, any influences, equality of effect. It is necessary to consult a thermodynamics database that has information about cadmium to determine that the melting point of cadmium is 321 degrees Celsius and the vaporization temperature is 767 degrees Celsius. Thus, the final equilibrium state in its new surroundings is liquid cadmium. So the final equilibrated condition is from solid to liquid. So what process involved in this change? So what happens? What happens it is that the cadmium melts. The process involved in this change is a melting process. Melting process is a phase transformation in which the crystalline structure of solid cadmium is converted to a structure that is liquid. Pockets of the liquid phase nucleate and then forming a solid or liquid interface. The motion of this interface toward the solid phase increases the amount of liquid at the expense of the solid phase until there is no solid phase left. Practically speaking, a number of issues that are ignored in this simple description of the process also need to be addressed. Since the cadmium will melt, it has to be placed in a container, for example a crucible, before it is put in the furnace. Will the container react chemically with the cadmium? Also, cadmium vapor will form over the liquid. How high will the vapor pressure become? And then lastly, cadmium vapor is toxic. So significant precautions will have to be taken to contain the sample and its vapor. If the ambient atmosphere is air, will cadmium oxide or other compounds forms? Evidently, a comprehensive answer to the question, what will happen, requires answer to all of these questions. Thermodynamics has the power to address all of these issues. The scenario shown in figure in the previous slide can be used to frame a variety of rearrangements of the generic question, such as what surroundings 2 must be provided to convert system A into a specific version of system B. For example, what range of temperatures can I use to convert body-centered cubic iron to face-centered cubic iron? And then, what surroundings 2 must be used to prevent the conversion of system A into a specific system B? What surroundings must be avoided? For example, what range of furnace atmosphere compositions must be used to avoid the oxidation of a set of turbine blades during heat treatment? The apparatus of thermodynamics provides the answer to this kind of questions by providing the basis for determining the equilibrium state of any system in any surroundings. This figure provides a summary of the component parts of thermodynamics and how they fit together to produce maps that are ultimately used to answer practical questions. The concepts and connections in this figure provide a very useful basis for understanding the foundations of how thermodynamics works and will be referred to frequently as the arguments developed in this topic. The content of the field is contained in a few principles that are applied through a few strategies. So here are the principles that are applied through a few strategies. In phenomenological thermodynamics, each system is a structureless mug that is gifted with properties. As a first step, properties that make thermodynamics work must be identified and defined. Properties such as temperature, pressure, composition, heat capacity, coefficient of thermal expansion and compressibility, entropy, and various measures of the energy of the system. Definitions of properties are introduced throughout this part, as new system and surroundings variables are also introduced. You must also remember that the central principles of thermodynamics are three laws that will be described in the next topic. The general criterion for equilibrium, which came from the second law, is developed in the second main topic, which is equilibrium in thermodynamic systems. Since a primary goal of this part is the exposition, or in other words, written a description of equilibrium states that matter will show, there must be a basis for determining when a system is in equilibrium. Now the strategies. The conditions for equilibrium are a set of equations between properties of the system that must be satisfied when the system is in equilibrium. These equations are the basis for calculating maps of equilibrium states from database information. The list of equilibrium equations expands as the nature of the system under study grows more complex, requiring additional variables in the description of its states. This strategy is first applied to a simple system in the equilibrium in thermodynamic systems, also included in the second main topic in this subject. The same strategy for deriving conditions for equilibrium is applied repeatedly in the remaining topics as systems of increasing variability and complexity are treated. For databases, thermodynamics identifies the minimum information set that must be obtained to compute the properties of a system. The list of properties in this minimum set expands as the system under consideration exhibits more variables. For example, there are no composition variables in a one-component system, in this case, unary system, while heat capacity, coefficients of thermal expansions, and compressibility are sufficient to compute the rest of the properties of such a simple system. Additional information is required to treat systems that exhibit more than one phase. For example, solid plus liquid, which you will learn in the third topic of this course, which is the unary heterogeneous system topic. Treatment of multi-component system requires additional chemical variables with associated required database properties in multi-component, homogeneous non-reacting system solution topic. Further information is required to treat additional phases that a multi-component system may display, which will be introduced in thermodynamics of phase diagrams topic. The principles and strategies of thermodynamics provide that data into the practical form of equilibrium maps, while the map provides answers to what will happen questions. Examples of the maps are shown in the bottom row of this figure. So we have here the phase diagrams, the gas phase equilibria, the predominance diagrams, the defect diagrams, and last but not least, Pourbaix diagrams. So I will explain each of the maps of these equilibrium states, starting with the phase diagrams. A point in the phase diagram represents the equilibrium structure of a particular material composition at a particular temperature. The gas phase equilibria map displays the equilibrium composition of one of the components in a mixture of gases. This kind of map also provides the basis for the design of furnace atmospheres with control chemistry for heat treatment, coating formation, vapor deposition, and stoichiometry control. Predominance diagrams provide a reasonable approximation to the phase diagram in such complex systems and require significantly less data. These maps may be used in conjunction with a gas composition map to determine the range of elemental composition of the atmosphere necessary to produce each compound. An equilibrium crystal defect diagram is a database providing thermodynamic property changes associated with the formation of defects in compound crystals. And then Purbach's diagrams here is popular in its use in the analysis of corrosion behavior. These maps all share the attribute that they represent competition for stability or predominance among the various forms that the atoms of the elements in the system may show. To conclude, each has its realm or scope of applications that address appropriate versions of the question, what happens? Now we reach the part where the three levels of the thermodynamic apparatus. What determines how matter behaves? There are three levels of sophistication that are used in answering this question. Those three are phenomenological thermodynamics, statistical thermodynamics, and quantum statistical thermodynamics. The phenomenological description, in which matter is treated like a structureless mud that possesses a set of properties like temperature, pressure, chemical composition, heat capacity, and etc. The behavior of an evolving system is described solely in terms of changes in its properties. This level of description contains no information about the underlying structure of matter that determines these properties. Relationships between properties are described, but there is no attempt to explain the source of values of these properties. It only questions about what happens. Now, for statistical thermodynamics, the description which recognizes that matter is composed of atoms that exist in different structural arrangements like gas, liquid, crystal, molecule. The individual atoms have properties like size, mass, electronegativity, energy, and etc. Pairs of atoms, in this case bonds, have properties associated with the interactions between the atoms in terms of its bond strength and bond energy. The behavior of a system is derived by statistical strategies that connect the properties of these units to the properties of the huge collection of atoms that make up a system. This level of description provides an explanation of the phenomenological properties of the system in terms of the behavior of the atoms that compose it, which is why statistical thermodynamics always question about why does this happen this way. And finally, the quantum statistical thermodynamics, which recognizes that single atoms and groups of atoms have an internal structure mostly residing in the distribution of electrons in space and in associated energy in the system. This level of description explains the behavior of atoms and ensembles of atoms, and hence that of system at the most fundamental level. So, the quantum statistical thermodynamics is all about fundamental description. Among these three, phenomenological thermodynamics has been the most widely used level of description in the practical application of thermodynamics. The question, what happens, can be answered at the phenomenological level for very complicated practical systems. A description of this level of detail is sufficient for many, if not most, practical applications. The more profound question, why does this happen this way, which seeks a level of explanation of observed phenomenon, requires the statistical approach, and even more fundamentally, quantum statistical thermodynamics use this kind of approach. These fundamental descriptions rely heavily on computational materials science, in which the properties of large collections of atoms are computed from sophisticated models for the interactions between atoms in the structure. Explanations provided by these first principle calculations have the potential for provoking new insights that ultimately may permit the prediction of database properties that have not yet been measured, or the extrapolation of results for simple systems to more complex ones. Because thermodynamics identifies the properties needed to predict the behavior of matter, thermodynamics considered the basis for establishing the focus of these more fundamental scientific endeavors. So let us have a recap on what we have learned in today's video. So what we can conclude in our learning today, that is, thermodynamics provides the basis for answering the question. Remember the part that if you take system A in surroundings 1 and put it into surroundings 2, what will happen? Secondly, thermodynamics is important because it is pervasive, comprehensive, established the basis for organizing information about the behavior of physical systems and for developing maps of equilibrium states. And then, maps of equilibrium states are used to supply answers to the what happens question for a wide variety of systems in a wide variety of surroundings. And last but not least, the behavior of matter has been described at 3 different levels of sophistication. First is phenomenological thermodynamics. The second one is the statistical thermodynamics. And finally, the quantum statistical thermodynamics.